Okay. Joe Huba is the primary architect of the simulation code that I'll be talking about. Richard Denton is also on the Plasmasphere team. He gave us some nice RPI data. Jeff Crowley is on our ion neutral team, and he gave us some output from the time GCM code. Taiwei Wu is also at Naval Research Lab. She helped with code coupling. So this is the outline of what I want to talk about. First, I want to talk about the SAMI3 code for those of you who are not familiar. It's a model of the ionosphere, but it's also a model of the plasmasphere. It extends way out into space along the geometry is all along field lines, and the field lines extend way out into space. It's not like time GCM where there's a ceiling on it or anything. And then I'm going to then go on to show from the simulation that the shape of the plasmasphere, at least the simulated plasmasphere, is affected by the thermospheric winds. We change the wind model, the shape changes. Then I want to compare the data to try to convince you that you should believe us. And then I want to talk about the dominant mechanism shaping this, which turns out to be the wind-driven dynamo. I gave a version of this at AGU, and at the time I thought it was something different, so that part has changed. And after we changed it, then we sent the paper in. So the SAMI3 code, there's a number of versions of it. This version has a very simple magnetic geometry. It's just non-tilted dipole, which made it easier to get the plasmasphere working in this code. Its interhemispheric plasmas flow back and forth through the plasmasphere to the two ionospheres. It has 7 species. The important ones for these are hydrogen, helium, and oxygen, but I'm mostly just going to be talking about the hydrogen and the electron density. It's 3D, yes. Yeah, there's a version called SAMI2, which is a single magnetic plane, and you can download. That's open source, but 3D is global. It goes up to the poles. It has E cross B drifts in all the different directions. So each ion, oops, keeps pressing the wrong button. Each ion is a fluid equation, and they're all treated equally, and then the temperature is solved for some of the ions. The plasma motion perpendicular to the field is all E cross B drifts, and it's in all directions, including zonal, which some of the older codes didn't have. The neutral winds come from a model. Here we talk about HWM93, but I'll be switching models as we go through. So those are the equations. Just for completeness, it solves the momentum equation, including the inertial term. And then it has a wind-driven dynamo. It solves that self-consistently. The high-latitude fields come from the Weimer model. So it does not have a ring current. So we're going to focus on, so it's not really going to get storms right, but we're going to focus on a quiet period. So we're going to do this event. This is 2001. It's picked during a time when Image was up there taking measurements for us. And there's the storm. This is BZ, BY, density, solar wind. And there's a storm, BZ is negative, and then there's this long, quiet period. So we're going to focus on that. Just to show that we can do the storm, this is the storm. These are the potential mapped out to the equatorial plane. So this is hydrogen density in the equatorial plane. The sun is over here. And during the storm, we get something that looks kind of like a drainage plume. So we capture some of those dynamics even if we don't have the ring current. But we wanted to focus on the quiet period, and the first simulation, I'm going to do 4 different cases with different winds, and then a couple of variations. And the first case, I'm going to start baseline, no winds at all. So with no winds at all, this is the equatorial density, and electron density, equatorial plane, every 8 hours, so this is over 3 days, and this is the profile at L equals 4. And what you see is it's very round. And a couple of days ago, Jerry Goldstein asked why the plasmasphere isn't round. Well, when you have no winds, it is round. I'm going to make these things in the corner bigger and put in this circle is actually a contour at a fixed density of 300 cc, I think. And these profiles, I think this is this one, so this is the long dashed line. But you have a very smooth profile versus local time. So it's very round. So when you switch on the winds, and these are 2 different cases. This is HWM93, which is an empirical wind model. And this is time GCM. You get, it's no longer round. You get these shapes. And you can verify that because this is the profile at L equals 4 for each of these 3. And you can see that you have a shape. here. And for time GCM, you have a different shape. So you put in the winds, you get a shape, you get a different shape if you change the winds. Just blowing up the last row of the HWM93, these are 3 of these things. You can see that the shape is changing with time. This is every 8 hours. And this is, again, this profile of density at L equals 4 in the equatorial plane versus local time. And you can see when UT changes by 8 hours, this shifts by 8 hours. So basically what you have is a profile that is moving with the Earth. So that's the argument that the changing the wind model changes the shape of the plasmasphere. Now let's get on to the measurements. Image RPI did these passes through here. So this is an example of 2 different passes. It sweeps through L, it sweeps through magnetic latitude. They're approximately constant local time. So if you go through these, and this is one early on when it's eroded, and this is one 3 days later, 4 days later when it's filled up again. And so if you go to a given L value and look at each pass, you can look at constant L, constant local time, and approximately constant magnetic latitude. And so we will plot the SAMI3 density at constant L, constant local time, magnetic latitude, and compare it to each of these passes through there. And so that's this. And so these points, this is for L equals 4, this is for L equals 5.4. The points are the image points. The curves are the SAMI curves, and this is no wind. So with no wind, it's all very flat. We have a round plasmasphere. With HWM07, which is another empirical model, you get these wiggles. 93, you get different wiggles, and time GCM, you get different wiggles. The size of the wiggles is about the size of the variations in the densities. But if these daily oscillations are there in the actual data, it's not resolved. We don't sweep through the plasmasphere often enough to resolve the oscillations, but the size of the wiggles in the data are about the size of the wiggles in the simulation. So that gives you some suggestion that maybe we're in the right ballpark, but it doesn't definitively show that this is exactly what's happening. So now we wanted to think about, okay, what's the mechanism? And so this is one of the pictures I just showed you. This is for the HWM93. Those are the wiggles. Those are the data points from each sweep through the plasmasphere. And this is at 3:51 local time. We have a similar curve for the other side of the sweep through. So the thermosphere acts on the ionosphere in 2 different ways. One is it directly pushes ions up and down field lines. And so that's through a force, the ion-neutral collision force. And the other way is there's a dynamo. It runs a wind-driven dynamo and causes E cross B drifts to go up and down. And so we did one run where we turned off the ion-neutral force, thank you, and we did another run where we turned off the dynamo. And what you see is when we turn off the dynamo, it looks an awful lot like the no-wind case. So that's a clue. Turn off the ion-neutral force, not much happens. I could skip that, but it just shows that it gets round again when you turn off the dynamo. So now we're trying to get a handle on this. And these are the TEC maps for all 6 cases. These are 6 different wind cases: no wind, HWM07, time GCM 93. And these are the 2 variations on 93. This is the one with the no dynamo. And you can see that no wind and no dynamo cases look pretty similar, but it doesn't tell you why these 2 cases are giving you a round plasmasphere. And in fact, when you look at the refilling, you see that the refilling is very steady. Actually, if you go up one plot, you can see that these curves, 1 day later, 1 day later, 1 day later, at all local times, their curves are all going up together. The refilling is very steady with the dynamo turned off, and in the case with all the winds, you can see that the refilling is stronger where the density is higher. So we looked at the TEC up at a L equals 4.8, which for a non-tilted dynamo is a straight line, so that's there. And the no wind case and no dynamo cases were actually the highest TEC values, but it's not dramatically different from the other cases, so it doesn't really tell you why. Then we looked at the outward flux of hydrogen ions, and to simplify things, we averaged it over longitude, over the azimuth. And then we looked at the peak outward flux within the L values that we were interested in between 3 and 7. And we plotted it as a function of time. And the no-wind case is wiggling around in here. The no-dynamo case is very strong. The HWM93 gets up just as high as the other cases, if not higher than the no-wind case, but it keeps dropping down. And what's basically happening is that the position of the peak outflow is moving from the area of interest between L equals 3 and 7 and down again and then back up again and down again. It's like there's a hose refilling the plasmasphere, but the E cross B drifts are moving that hose around. And those are the discussion points. It's pretty much the same as my outline, so I've already said it. So thank you. Let me hand that man a microphone.
Jonathan, so in the runs, my assumption is that you used a fixed convection electric field.
Oh,
from a Weimer model or something.
Well,
like that?
we used the Weimer model. It's driven by the solar wind, and basically for the purposes of this, it was useful for eroding the plasmasphere at the beginning of the simulation, but during this quiet period, it kind of got out of the way.
Well, so my question was, what did you assume for the potential drop, say cross-tail potential for the quiet time, and what do you think would have been the effect if you just changed that potential drop by, say, plus or minus 5 kilovolts?
We did not include that. Basically, if we had like an RCM type model, that would have that effect. So whatever that would give you, we're missing it. Okay. Sure.
If you could indulge me for a second, I'm a fan of recursive names. If you could tell everybody what SAMI stands for.
Oh, SAMI2 stands for SAMI2 is another model of the ionosphere. SAMI3 stands for SAMI3 is also a model of the ionosphere. So it's a Linux-y kind of thing.
Thank you very much
Thanks.
for indulging.